Okay. Class already once. Huh? Don't take again. Okay. Well, this is not OFDM system, but this is a classical single carrier type system. Of course, the input to the MRA modulation is what? Information bits. Okay. And the demodulator gives an estimate of the okay, this is a typical link. Of course, channel coding is not considered here. All okay? Yes. Okay. What is MRA modulation? Information bits are coming in, a sequence of ones and zeros. Then what do you do here? Huh? Yeah, what happens here? Yeah. Log m base 2 bits are taken, right? Take log m base 2 bits, it could be 3 for m equal to. These 3 bits appear as C0 is what? It's a complex number and it's taken from an MRA constellation with points. It is, for example, m equal to 8 PSK. Take these bits, map them to a constellation point, which is a complex number, and now this becomes your new information, right? The information is in binary domain, and then now it changes to sequence of complex numbers. Of course, if this is a discrete random process, this also becomes a discrete random process based on the characteristics of the input. Okay, so this sequence is a discrete random process with some variance. We model CK as, let's call it. But use the symbol A, I believe, the moment. Just keep it CK. Okay, CKR 0 mean IID symbols. CKR, its model as CK is 0 mean IID what is IID? With identical distribution. Okay. And with variance sigma C square, that is expected value of CK absolute value square, where we are assuming mean is 0. Okay. That's the general assumption. Okay. Of course, you can have sequences that are correlated. Now, if you pass this sequence through some kind of a discrete filter, then they become correlated objects. Okay? Pass CK through a time domain filter, obviously the output will be correlated. But that's not the point here. In this case, now it carries information. Obviously, you cannot transmit numbers, right? Transmit just one sequence of numbers? No. A lot of things that need to perform before you transmit. A lot of times people think that I'm going to transmit 1 and 0. Actually, you don't physically transmit 1 and 0, you're transmitting 1 and 0 some waveform. Okay? So there is nothing, so we call it digital communication system. There's nothing digital here. Everything is analog. Analog in nature. So the next thing that comes into picture is a transmit filter. PK is a zero mean IID process. What would be the power spectral density of this band and the power spans? Right? Because it's a white, it's an IID sequence. The autocorrelation function is a delta function. The value of K and C conjugate K plus M, which is R of M, is equal to delta the autocorrelation function, and R of M is equal to sigma C square for M is equal to 0 and it is 0 elsewhere. Now, if I take the Fourier transform of this autocorrelation function R of M, I get the power spectral density in this discrete random process, right? Fourier transform of R of M gives you the, I think you probably have to, yeah, this is fine, right? Power spectral density S of F of this process, and you know that the power spectral density for this is flat and it has frequencies everywhere. So therefore, we put a transmit filter to limit the spectrum. Okay? You need to put a transmit filter. Of course, that's not the way to explain it, but you always need a transmit filter such that the low pass signal at this point occupies certain bandwidth. I mean, let's talk about at the baseband level itself. I want the signal at this point to occupy certain bandwidth. Okay. Of course, we'll talk about the notion of bandwidth a bit later, because the definition of bandwidth, there is no universal definition for bandwidth. Right? The signal doesn't decay to 0, then you can't strictly define bandwidth. Talk about 3 dB bandwidth, 99% bandwidth. So obviously, we need to restrict the transmitted signal to a given band. This is generally the case in almost all systems. Wireless, wireline, whatever it is, you have to restrict the signal to some band because you are allowed to operate in that given band. So basically, you want some band, let us say 200 kilohertz, for example, and 200 kilohertz. So your channel width is 200 kilohertz. We'll do everything in baseband form. Okay, and we'll talk about the upconversion. 200 kilohertz is your band, so your signal should be confined to this. Well, we may say, well, if our signal doesn't decay to 0, obviously it will have a tail that goes beyond 200 kilohertz that manifests as adjacent channel interference. If at all this is upconverted to some carrier frequency F1 and the channel that lies on F2, which is 200 kilohertz away, or 100 kilohertz away on one side, then it will appear as so one of the most important quantities is of interest. Signal that is transmitted has a power spectral density. Okay? Well, actually, it should be called average power spectral density. The reason is that talking about transmit signal is itself is a realization of a random process, and we cannot talk about Fourier transform and squared Fourier transform for a random signal, because if you take a piece of a random signal and take the Fourier transform and square it, that doesn't give you the same picture about the frequency current, because you're still taking one snapshot of the signal. So you have to average it over the ensemble of waveforms, or you have to take one piece of the signal, take the Fourier transform, square the magnitude, and you take another piece, and so on and so forth, and average all these various quantities for multiple checks. That's because you want to average the randomness contained in the signal. So it's basically an average power spectral density. That is the average amount of power contained in any band of width delta f. If you take the average power spectral density and take a delta f band, and if you make a measurement on the power, and this area will give you the average power contained in the. So now we will take a classical single carrier system, okay, and we will work with the classical single carrier system, and we'll talk about the average power spectral density of this single carrier system. We'll call the signal at this point S of t, which is the low pass equivalent signal. S of t can be generally written as let's not yet call it S of t, but we'll call this S C of t, which is still C denotes the baseband signal. That is nothing but C of k, P of t minus kt, k ranging from minus infinity to plus infinity. What is this? Can you tell me? What is capital T here? Time period of what? Let us say P of t takes its following form. Amplitude A. Then what would the signal look like? Of course, this need not be T, but I have just chosen it to be T. Arbitrary pulsing, right? Flat. Why it is flat? Theta is taking values from the MRA constellation, random values. So you will have a waveform T0, T1, T3, and so on, so forth. This is SCR. Obviously, C0, C1, and C2, so on, so forth. They are complex numbers taking from MRA constellation. If at all we use a pulse P of t, not in this shape, but let us say takes a shape minus t to, well, minus t by d2 plus t by 2, then we would have something like this. Is that right? Huh? Then if you have a sync pulse, obviously sync pulse has infinite support, a single pulse, then it is a sum of shifted version of the base pulse P of t by an amount t with the weights k. Obviously, you may say why you put minus infinity plus infinity, it should be between 0 to 10 or something like that. That's highly secondary. Time slot. Obviously, you are restricting yourself to some finite values of finite range k equal to 0 to 1. Okay. Now, I can write C of k as ak plus j times bk, where j equal to square root of minus 1. So this becomes k equal to minus infinity to plus infinity, ak p of t minus kt plus j times another summation. Instead of using the index k, I will use L. Okay? Just writing it in slightly different form. So this is the baseband representation of digital modulation. Okay, now you tell me what is the data rate, or let's call it signaling rate. Signaling rate here is, or baud rate, 1 over t. Rate is 1 over t. That is, every t seconds you are transmitting one complex signal. Okay? And what is the data rate in bits per second? You are setting log m base 2 bits using one complex symbol. So logarithm of m base 2 bits are transmitted in 1t. The rate is make sense? Doesn't make sense? Log m base 2 divided by t. Data rate is, bit rate is, the units here is bits per second, and the units here is symbols per symbols. By symbols we mean modulation. Okay? And you see that this quantity is fundamentally related to the bandwidth of the system in some ways. That will come in a bit later. And one might wonder what should be the bandwidth of the system. Well, that really depends on the pulse you are choosing. If you have a rectangular pulse, what would be your bandwidth? Theoretical infinity, but you can choose it as, if you take one side lobe on each side, 2 by t or something. by t. That means your baud rate is 1 over t, but your occupied bandwidth measured in hertz is 2 by. But if you use sync pulse parameterized with t, then what will be your bandwidth? P of t as a sync pulse, sine phi. P of t is sine pi t by t by t by t. Then what will be your bandwidth for this type of system? We don't know. We haven't evaluated the bandwidth, but hopefully it is 1 by. It is. So now the question is, the bandwidth is obviously related to the power spectrum of signal. We have to calculate the power spectrum of SC. Calculate the power spectrum of SC. So I'm not going to do that exercise here, but that will be your first assignment. Submit it. Same time. SC of F can be shown to be, I'll give you the answer, but you'll have to prove it. Okay? C square divided by T, Fourier transform of the pulse P of T, absolute value square, is mu of C value square divided by summation over k equal to minus infinity to plus infinity of by t value square multiplying, I'll write the multiplication factor, delta f minus by t. Should go there. C square is expected value of a square is expected value of C. Of course, we are assuming a Whiteson stationary process. Okay. And P of F, the Fourier transform of P of T. What do you learn from this? Spectrum has a continuous path and a body. Series of impulses, discrete path. And do you want the discrete path to be present? Desirable. Well, usually it's not. It's just a waste. So, if you want to eliminate that discrete path, what do you need to do? No, this is the power spectral density for the case where Ck is a Whiteson stationary discrete process. Ck is a discrete Whiteson stationary discrete random process. Results hold for the case where Ck is Whiteson stationary. Of course, it's a discrete random process. Okay. Well, in this case, CKR IIT. Of course, we did not make here. We do not make any assumptions about the variance. They can be argued. So, if you want to eliminate the impulses, what do you need to do? So, if you choose the mean to be 0, it will eliminate the line components in the spectrum. That's why we always want to choose a 0 mean process. Because mean doesn't really convey any information. It doesn't convey any information. Part that really matters. Okay. So you can generally choose mean to be 0, and then we end up with sigma c square by t E of f whole square. So now, who dictates the power spectral density? E of t solely dictates the power spectral density. Okay. Of course, if C of k is IID and it is spectrally flat. If C of k is not spectrally flat, that means the autocorrelation of C of k is not an impulse function, then that will also has an influence. That will also have an influence on the spectrum of the transmit signals. Okay. That we will not consider. Okay. So if you filter C of k through a filter, discrete time filter, that is going to alter the spectrum. Which is like saying that anyway we have an input Ck, it is going through a transmit filter. So whether the filter is discrete time or it is continuous, it doesn't really matter. Both will have an influence on the spectrum. Okay. But in any case, in the homework, you will have to derive the autocorrelation function, and then you have to calculate the average power spectral density by taking the Fourier transform of the autocorrelation function. But you will see that Fc of t is a cyclostationary process. Okay? Cyclostationary process. That means its autocorrelation function is periodic in capital. And for a cyclostationary process, go back and read Propolis if you have any doubts. They have been covered in probability and random process course. Not go back and learn all those things. Question of autocorrelation function and average power spectral density cyclostationary process. You should not the course to teach. Okay, so for the next class, you should know all about this. Submit the homework with the entire derivation. Fine. Now that we know the average power spectral density for the baseband or low pass signal, we can talk about the average power spectral density for a signal which is upconverted and transmitted. Okay. So what do you do for upconversion? Yeah, so mathematically speaking, you multiply this with so S of t, of course I have not shown it in the block diagram, is obtained by taking SC of t multiply with e to the power of j 2 pi fct, and then you take the real part of this entire signal. I think I have told you or some other students several times, there is no such thing called transmitting the sound. You can't transmit completely. Transmit must be real. It has to be real value, and you should be able to size it using a circuit. So you cannot transmit SC of t into j2 pi fct because it's a complex value signal. You cannot transmit such things. So you transmit only the real part. And that turns out to be, if you write it in terms of this multiplied by e to the power j 2 pi fct and you take real part, what would you get? So my ak p of t minus kt, k ranging from minus infinity to plus infinity. The whole thing is multiplied with cos 2 pi fct plus or minus pl p of t minus lt, l equal to minus infinity plus infinity by with sin pi fct, where fc is the carrier frequency, much higher than bandwidth of c. Okay. Now you can think of this being the real part and this being the imaginary part in the low pass representation. Exactly how you would develop synthesized signals if you want to realize a communication. Okay. This is what we receive when you transmit to a medium. It could be wireless or wireline, whatever it is. Then you will receive it and receive the signal, receive it along with some noise, thermal noise. Okay. Then you will apply a filter. First of all, before you apply a receiver filter, this is baseband. You get this received signal along with noise, and then you down convert it into baseband form. That means you are going to select this part and this part by applying suitable down conversion. Then you will collect the real part plus j times imaginary part plus some sort of a noise which was at fc, and then it comes to baseband. Then you apply a filter. We'll talk about the choice of this filter. Right? By filter we mean we are trying to filter out something. Then you'll be ready to make decisions on CK. Okay? You can collect your complex data CK, filter, output. Perhaps I should write this as sample this probably at T range. Right? Sample this at okay. So what is the spectrum of the actual transmitted signal? We talk about the spectrum of the baseband signal. We have conveniently represented. What is the spectrum of the transmitted signal? Any idea? That's what we are really interested in, right? We are interested in the spectrum of S of t. We are interested in the spectrum of the transmitted signals, and that would be S of f, and you can show that S of f is equal to 1 divided by 4 SC of f minus fc SC of minus f minus What is this? The baseband spectra is in this particular form. This SCFF and the RF spectra is centered around FC, centered around minus FC. One by two. Check this out. Okay. Okay. Now, if you are given only the band given to allocate it to you, everything else that falls outside this band is interference to else who occupies the portion. Sometimes you may want to use broad bands between two channels, but that's up. You may not always get those broad bands. So, for the transmitter, the real test is whether it conforms to some mask of this kind, which is called the spectrum mask. The regulator gives you what is called the spectrum mask. Spectrum mask is usually defined at 0 dB, and this is at some other level, let us say minus 20 dB or minus 30 dB, at minus. So your signal will occupy like this. At any point, it should not go beyond the mask. But this mask is defined in a certain way. There is a definition for the mask. See, you have normalized the speed to be 0 dB. But once you normalize your signal to the same levels, at no point you should exceed the mask. If you do, then you are not permitted to. Spectrum mask compliance test. Build a transmitter, it has to be. That's very, very important. So if you have any non-idealities in the system, and if it, for some reason, if your spectrum mask, if you violate the spectrum mask, one nonlinearity that comes into is the power amplifier, RF power amplifier. That is the last step in the communication chain, right? If you have to transmit it, let us say 10 watts, you take the baseband signal and you have to amplify it to 10 watts power, and usually these amplifiers are highly nonlinear. Why is that? They distort the signal, and the distortion manifests as a spectral regrowth. By spectral regrowth, you have to be very, very careful. Okay? Of course, there are other criteria you should also conform to. For example, the real and imaginary parts of signal, that is the sine and the cosine branches, should have the same gain. Real part and imaginary part should see the same gain. If at all in the circuit, if the Sine branch, after demodulating, this has a different gain compared to this, the constellation will be distorted because real imaginary parts are skewed. That's called IQ imbalance. The transmitter must ensure that the real imaginary parts are not overly skewed. Okay? That's because of various impairments in the transmitter. For example, if your crystal oscillator gives you cosine 2 pi f ct, from cosine 2 pi f ct, if you don't construct sine 2 pi f ct perfectly, then problem. How do you get sine 2 pi f ct from cosine? Yeah. What kind of circuit is needed? A Hilbert transformer. That's again a circuit. If at all that has an non-ideality, then your generation will not be formed. There will be some leakage between I and Q points. Such impairments, you have to really keep them. There are many other impairments. We'll discuss them as and when time comes. Now I think you should know meaning of data rate, bandwidth, or spectral density. Isn't it? Class where no one had a good class to be in. Imagine speaking for an hour and a half in my shoes. Class has undergraduate students. They'll ask me some question or the other. Ask a stupid question. Otherwise, it is easy to teach because people have some basic knowledge. First course is unfortunately people can't question. Anyway, I should ask you for a few questions. Just okay. Well, then there is our friend noise, right? That's something we really need to understand before we proceed any further. So where is noise added in the receiver? Added in the receiver. What of the receiver? Something could be added there. Or what is the first step in the receiver? First, the signal received is amplified. What is a low noise amplifier? The name itself. The low noise amplifier. Name itself suggests something. Second step. After low noise amplification, what does it do? Noise amplifier, what does it do? Down converts. Name suggests it amplifies. It amplifies with minimal noise addition. Okay? There is a signal coming in. Here we have S of t plus some n of t. Then we have some alpha times S of t, which is amplification factor, plus n tilde of t. Amplify the noise by factor alpha, but it adds more noise because it's going through an additional circuitry which adds its own noise. So it is indeed S of n of t plus n of ln a of t in some sense. Well, it's not really like that, but just you can't really write it as additive. Maybe in this case it is, but just a low noise amplifier brings the signal level received, because at the end of port the signal strength is too weak because it has gone through the propagation medium and gets attenuated. As long as the signal level is above the noise power level, you can always demodulate. That's all we care. So what you need to do is you bring it to a voltage level which your circuitry is comfortable with. Okay? It brings it to a voltage level that your subsequent circuitry can really work with. If it is too weak, the circuitry, because the circuit has a dynamic range, plus or minus 1 volt or something like that. Okay? So the next subsequent circuit is. So then you can do mixing. By mixing we mean multiply this with e to the power of minus j 2 pi fct, of course. That you can do because that's a receiver operation. Or you multiply with cosine and then you also multiply with sine and then you put some kind of a band pass filter. Next, multiply this with power of j 2 pi fct, then pass it through a band pass filter with some bandwidth a bit higher than the. We are talking about a direct conversion receiver. In the world, not so long ago, people used to down convert FC to some intermediate frequency, 70, let's say 75 megahertz or something, and then down convert it to baseband. So they used to bring it to baseband in 3 different steps. These days, there are now direct conversion receivers. They come from, okay, you put minus here, let us see, from RF to baseband directly. So in that case, you can think of it as a low pass filter. That is nothing but you can think of this filter as this filter, or it could be a different filter which could operate in analog, or well, this is analog, right? The input is analog. The filter is also an analog filter, unless you do a sample and hold. Then it becomes, the output becomes. Okay? So it's really up to you how you build it. This can be completely analog with a little bit higher bandwidth, and then you can have ADC output. So you can think of this as low pass filter and then ADC, but ADC in itself is a low pass filter. You can think of it as a low pass filter because, or you can, so it's really how you build it. Okay? So this gives you samples at any rate you want, which could be 1 hour. And once you have these samples, then you go through normally what is called an equalizer or demodulator. Or if it is a complex, the channel is ISI, you equalize it and then demodulate it. So sometimes this module can be skipped depending on. Yes, of course. Slightly relate to that, and you may ask, how do you obtain this T? You need to have a clock that generates this T at the receiver that is very tightly aligned with the clock at the transmitter. Of very high accuracy to do it. Otherwise, you need another circuit to generate a clock at frequency 1 over T, and usually that frequency, that clock is derived from FC in itself. So FC, and if you generate FC which matches with the FC at the transmitter, then from FC you derive the clock 1 over T. So you don't, they're sort of dependent. And how do you generate FC? It's a crystal oscillator. These days you use very high quality crystals, very highly stable crystals. They don't drift too much. Then if they don't drift too much, they can assume that this is matched to the transmitter, and then 1 over T also you will get it. But nevertheless, there is always some difference between this T and that T by small. That you will have to compensate. Low data rate modems, clock drift is not a very big deal, but when you go to high data rates, it's very sensitive to. But anyway, we won't go through all that in this course. We sort of idealize it to the extent we can. Now, the aim for me is to model the noise. Without noise, really, there's hardly nothing. There are hardly any challenges in some sense. Right? Noise that makes this problem. Okay, you must understand that noise is added everywhere. It is added here. It is added in the. It's called a mixer. In the mixing process, noise is added, and here, if it is an analog filter, noise is added. The only place noise is not added is in the digital discrete time portion or the digital portion, where the addition, it's not the noise, but it's the quantization that kind of that's impairment that comes into picture, but it's not the noise. Okay, so we have three sources that can contribute to noise here, here, and here. So the noise at this point, power, is it higher or lower than this? Higher. So a receiver has what is called a noise figure. And a receiver is characterized with the noise figure, that is the signal to noise ratio at the, it depends on how you define it, at the output divided by SNR at the, that's defined as the noise. So SNR at the input by SNR at the output. The reason that they differ is that, of course, these are RF terms. It's not defined in baseband quantity. That is up till this point. So noise figure is a very important metric because the cost of the component can dramatically increase if you want the one with low noise figure. Ideally, you want this to be around 1, but you can never have a noise figure of 1. So usually a receiver has a noise figure of around 8 to 9 dB. That is so much noise is added. Well, I think these days you can also find 6 dB noise means you are adding 4 times more noise same compared to and not equal to kdB. There is original noise coming in, and then each module add some more noise, and you keep on adding more and more analog elements. You keep on adding more and more noise. Of course, there is a formula to calculate the noise figure. You have a cascade of. I've done that. Repeat it. Right? If you have a cascade of filters, each with its own noise figure. Then you can calculate the noise figure for the whole system, right? So this is done. Okay, we'll not do that here. So what is really of interest here is how to model the noise that is actually coming in the very beginning, and then you just take into account the noise figure. You don't worry about exactly how many components are there and how they are adding it. For a system designer, you just specify the total noise figure. That is noise figure for this from here to here, and then you take that into account in your link budget calculation, which you will do. How many of you know how to model N of T? N of T? Do you agree with this? Why is that? Because noise is added to the signal, and signal is at FC. So noise should also be at FC. It can be written as and the real part of soul thing. Okay. Now we need to characterize Ni of T and Nq of T. Okay, and that gives rise to N of T. So we'll characterize Fni of T and Fnq of T. Or rather, we'll drop this. Well, okay. Characterize that. First of all, we should note that the power in this total signal N of T variance of one sample of N of T. Okay, that's what is equal to variance of okay. Ni of T and Nq of T are statistically independent Gaussian random processes. Statistically independent Gaussian random process. Okay. For a given T. Now, Ni of T it's an analog signal, it's a random process. It is described as a multivariate Gaussian distribution. What is described? The samples of Ni of T, sample this, we take a collection of samples. We take the samples of this noise They form a multivariate Gaussian noise distribution characterized by, well, basically they are IID noise samples, each with Gaussian distribution, zero mean and some variance. They are IID Gaussian, of course they are real signals, zero mean and variance, right? And it's the same variance for any sample. And sigma ni square and sigma n square are equal. Okay, this is a mathematical description. I am not getting into the physics of it. And the fact that Ni of t or IID zero mean some variance, autocorrelation function of Ni of t is a impulse function. The autocorrelation function comfortable with these notions of autocorrelation function and power spectral density? Is delta of t and the power spectrum of Sn of t is, well, you put a band pass filter the receive chain, right? Or low pass filter. At the output of the low pass filter, if you don't put any filter, obviously the spectrum is minus infinity to plus infinity. That is the power spectral density. But in the receive chain, the moment after, even the low noise amplifier, it has its own bandwidth. Of course, it's very wide. The subsequent module in the receiver, after the low noise amplifier, there is a mixer, it has its own bandwidth because it's a circuit. After the mixer, there is a low pass filter. If you look at the output of the low pass filter, assume that it has a bandwidth B. Okay? So, we filter this noise. Noise is essentially filtered with some low pass filter with bandwidth B. So, the input to the filter is additive white Gaussian noise with flat spectra, and output is, and we assume that the low pass filter has a flat spectra. Take an ideal low pass filter with bandwidth B, okay, whatever that B is. If that is the case, then the output noise is also additive white. Well, it's not white anymore, it is restricted to a band. So, Sn of f, draw it like this in the shape, minus plus Fc minus Fc, Sn of f, so bandwidth B, bandwidth, and the noise spectral density here is 0 by 2, 0 by 2, N naught is K T into B. Total noise power is N naught. Right? And K is the Boltzmann constant. And its value is 0.3 10 raised to minus 23 joules per Kelvin, and T is at room temperature, that's taken as 290 Pascal. Take it as 90 degrees. Equal to 17 degrees. Okay, you can choose any temperature you want. And the density, power spectral density is expressed as KT by 2. This is the density. KT by 2 is the density. It's independent of bandwidth. Okay. Well, this I will take it as a reference temperature. Yeah, it's called a reference temperature. Of course, there are two representations. There is a spectral representation for noise. Okay, and the total noise power contained is K TB. That is a variance of the complex Gaussian process Ni of T plus J times Nq of T. So half the power is contained in the real part and half the power is contained in the. Okay. Make sense? Okay. So this is KT by, that is the density without taking into account the filtering, right? So you can always put some virtual bandwidth here, KTB by 2. But I see, in my question, then what is this noise figure? Okay, this is somewhat idealized. At the input, there is what is called noise spectral density to the receiver because there is no filtering yet, KT. Then, in different chains of the receiver, more noise is added. Okay, and just before the baseband, the discrete time baseband, you take the total noise into account, right? So that's so using the noise figure of the receiver as a metric, you add this extra noise. So this calculation holds in an ideal sense at the front end to the receiver, if there, as if there is a band pass filter of bandwidth B, ideal band pass filter of bandwidth B, a noiseless band pass filter in some sense. That is it. Okay. So, but in reality, you have a whole lot of components, they'll add their own noises. But nevertheless, at each stage it is AWT. Okay, so when you do the link budget, all you have to do is calculate KTB, that is the noise power, given the bandwidth, and you calculate the received power, however you calculate it, and then you know the signal to noise ratio, and then subtract noise figure from it, because your signal to noise ratio dips because as it goes through the chain, you add more and more noise. That's all. That's how you calculate. Right? You know the noise power, you know the received power, then you get the signal to noise ratio at the input to the chain and subtract the noise figure from it. Well, I mean, by subtract I mean in decibels. Being in decibels, the other one being. Okay? Otherwise, it's much. Okay, we'll have an exercise to deal with it. The thing is that we always deal with dBm. What is dBm? What is dBm? Yeah, 10 lakh original power divided by 1 milliwatt. Otherwise, you write the power in milliwatts, take 10 log of it. 10 log power in watts divided by 1 milliwatt gives you power in dB. If the power is 1 milliwatt, how many dBm? Huh? Power is 1 watt, how many dBm? Okay, just give you an example. Let's take the reference term n naught equal to KTB, right? Let's work with the density not equal to KT for the time. Okay, the density. Well, actually, power is KTB and n naught is sort of denoted as KT. Okay, so just total power sigma square equal to KTB. That I will write it as K into the reference temperature TR, the actual temperature T by TR into the bandwidth T. Okay. Now I will write this whole thing in dBm. Sigma square dBm given by 10 log base 10. Obviously, base is important. Sigma square by 1 milliwatt. That is equal to 10 log base 10 K into TR, the first term, divided by 1 milliwatt plus 10 log T by TR plus 10 log base 10 bandwidth in hertz. Okay? Bandwidth in hertz. Remember, you don't divide all these by 1 milliwatt because it's already taken into account. Okay? Can't divide this by milliwatt. That doesn't work. Okay? The reason I do this is equal to, first term is equal to famously minus 174. This term is, how do I know? I know the Boltzmann constant. I know the XTR here, reference temperature, which is 290 or 70 degrees. Plus 10 log T base 10 plus the sum term F. Okay? TR is equal to 290K, and if T equal to TR, then the noise power sigma square in dBm is, and bandwidth assuming to be 30 megahertz, sigma square dBm is minus 99 dB. What does it mean? Your received signal power must be above minus 99 dBm. 8 or minus 97 or minus 90, something like that. If it is beyond that, if it is minus 110, the signal to noise ratio would be, if it is minus 109, signal to noise ratio is minus 10. So if it is received signal power is PR in dBm equal to minus 89 dBm, then SNR would be how much? Huh? This minus this in decibel, that would be PR in dBm minus sigma square dBm, that is equal to 10. Okay. That F can take into account increase in the noise due to temperature as well as the noise figure also. Okay, so you can lump the noise figure also as part of F. Okay, noise figure is 6 dB, you can just add it, or 8 dB, you can add it. Okay, so we sort of look at two different things here. We looked at baseband part of the communication chain, and we briefly touched upon various analog components here and there. Right? We talked about noise modeling, we talked about right? The RF. More things we need to touch upon before we proceed with the wireless part of it. There's nothing wireless in there. So we'll talk about the Shannon's capacity for any system. What is Shannon's capacity? Per, if I remove this P, this becomes bits per. Also write it as log of per what? Simple. Well, you can call it bits, I guess, but it's actually bits per unit time duration. We call it bits per second. If I send BPSK, how many bits per sample we say? BPSK, how many bits we say? The SNR of the channel is 1. How many bits you can transmit? Of course, I'm going to write it as base 2. SNR is 1. What is the capacity of the channel? 1. So if you transmit BPSK and don't receive any errors, then you achieve capacity. At SNR equal to 1, signal power equal to noise power equal to BPSK, there's a lot of errors, so you won't achieve capacity. So obviously, it's not a capacity achieving method, just plain BPSK without. Okay? But if you have a rate half turbo code, which transmit with QPSK, and if you can decode it without errors, and then 2 bits per second, it is Shannon's coding theorem. This comes out of nowhere. Nevertheless, that is the maximum data rate at which you can actually transmit. Not prove the Shannon's coding theorem here, but we sort of use it for system design. Okay? The maximum rate at which you can transmit and receive without errors. Of course, in the sense of transmitting a large frame of data, infinitely large frame of data, decode infinitely large frame of data, fight the noise completely. Okay? Get close to this. Happily, most communication systems have a lot of progress. Okay, we'll stop here. Stop it. You send me the CD tomorrow.